Hello, Saving Grace Homeschool. I'm James, and today we're going to be doing a maths lesson looking at numeric and geometric patterns. In this chapter, you'll learn to create, recognize, describe, extend, and make generalizations about numeric and geometric patterns. Patterns allow us to make predictions. You'll also work with different representations of patterns, such as flow diagrams and tables. So here's a pattern, example of a pattern. Going from one term to the next. Write down the next three numbers in each of the sequences below. Also explain in writing, in each case, how you figured out what the numbers should be. So, sequence A, over here, first let's read this, sorry. A list of numbers which form a pattern is called a sequence. Each number in a sequence is called the term of the sequence. The first number is the first term of the sequence. So here's the first term, and then it goes up from there in this case. So to do this question, we need to find the next three terms of each sequence, okay? So a good way to do it is you find the difference between each two terms, like this, okay? And you just need to do it a couple times to make sure that it is in fact a pattern and the pattern doesn't change after, like you can't just do one and then see. So the difference between 2 and 5 is 3. That's a 3. The difference between 5 and 8 is also 3. 8 and 11, also 3. 11 and 14, also 3. So you can see here that we're going up in threes. So the next three numbers after 23, because we know we're going up in threes, is going to be 26. Next number will be 29. And the next number will be 32. Please excuse my handwriting, it's quite difficult. Anyway, sequence B, we're going to see what we're going up in. This is just a way to represent it. You don't have to write it like this with these arrow loopy things. So here we go up by 1, then we go up by 3, then we go up by 5. Okay, we need to do a couple more. Looks like we're going up in odd numbers though. Then we go up in 7, and if the next one is 9, then we are going up in odd numbers. Then we go up in 9. Okay, so then the next one we go up in 11. And then the next one will go up in 13, so we get 53. And the next one will go up by 15. 53 plus 15 will give us 68. Okay, and then we go up by 17, which gives us 85. All right, let's move on to sequence C. So sequence C, we go up by 1, then 2, then 4, then 8, then 16. Okay, so this one, so we're going up in numbers, but we're also doubling numbers. If you look at it, so that's a different way to look at it. Sometimes the hardest thing can actually be just figuring out what the pattern is, and then getting the next three numbers in a sequence is actually quite simple most of the time. So here, if we look at it, all the numbers actually double the previous number. So we times 1 by 2, we get 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16, and so on. So the next three numbers are going to be 64 times 2, which is 128. I hope you guys are doing these yourself as well before seeing how I'm doing them. Then the next term is going to be double 128, which is 256. Oh, 256. And then if we double that again, we can get 512. Okay, now we look at sequence D. Okay, just by inspection, which just means looking at it, I don't have to write anything down here. I can see that it's going up by 2, goes up by 2, goes up by 2, goes up by 2, goes up by 2, etc. So then the next one, 19 plus 2 is going to be 21, plus 2 is going to be 23, plus 2 is going to be 25. Okay, sequence E, we go up by 1. Sorry, 1 first, then we go up by 2, then from 7 to 10 we go up by 3, 10 to 14 we go up by 4, and then by 5, and then by 6, and then by 7. Okay, so the difference between, if you keep going on this pattern, you'll get over here, and then you get 8, difference between 32 and 40. So now we're going to add 9, so we're going to get 49. Then we're going to add 10, we're going to get 59. And then we're going to add 11, which gives us 70. Sequence F, so we go up by 4. So here we go up by 4. Then we go up by 12. And then we go up by, okay, but already you can see, so this is 12, and then this is, you can see that you probably could use the same pattern, but there is an easier pattern in this case. What we are doing is we are timesing the previous number by 3. Okay, so 2 times 3 gives us 6, 6 times 3 gives us 18, 18 times 3 gives us 54, and 54 times 3 gives us 162. Then that times 3 gives us 486, and if we times 486, we can get the next 3 terms. So we get 1,458. Then the next one, if we times 1,458 by 3, we get 4,374. And if we times that by 3, we'll get 13,122. Okay, then looking at sequence G, just again by inspection, so you can check with this whole thing, but you can see straight away almost that the difference between them is 4 between all of them. Okay, so that means that the next 3 terms, 33 plus 4 gives us 37, plus 4 will give us 41, plus 4 will give us 45. Okay, and then sequence H, we have 2, 4, 8, 16, 32, 64. So that looks like the same as this one over here, sequence C, we just don't have the 1. So it's the previous number times by 2. So this number doubled. 2 doubled gives us 4, or 2 times 2 gives us 4. 4 times 2 gives us 8. 8 times 2 gives us 16. Then 16 times 2 gives us 32. 32 times 2 gives us 64. And then we can write the next 3 terms, which will be 128, 256, and 512. Then it says here, numbers that follow one another are said to be consecutive. Adding or subtracting the same number. Which sequences on the previous page are of the same kind as sequence A? Explain your answer. So you're going to have to look at these again, and you're going to have to figure out which sequences of the same kind as sequence A. Amanda explains how she figured out how to continue sequence A. I looked at the first two numbers in the sequence and saw that I needed 3 to go from 2 to 5. I looked further and saw that I also needed 3 to go from 5 to 8. I tested that and it worked for all the next numbers. This gave me a rule I could use to extend the sequence, and the rule is add 3 to each number to find the next number in the pattern. Tomorrow says you can also find the pattern by working backwards and subtracting 3 each time. So 14 minus 3 gives us 11, 11 minus 3 gives us 8, 8 minus 3 gives us 5, etc. So it's technically the same rule, they're just explaining it differently. So tomorrow looks at it by subtracting, and Amanda looks at it by adding. When the differences between consecutive numbers of a sequence are the same, we say the difference is constant. So that's like sequence A, when you keep adding 3 to each one. But it's not always constant. Like where was one where we added, one of them we added odd numbers. Am I right? Okay, here we go. I think it was this one. We added 1, then 3, then 5, then 7, etc. Anyway, question 2. Provide a rule to describe the relationship between the numbers in the sequences. Use this rule to calculate the missing numbers in the sequence. So you guys must write down the rule. I'll try to explain it. So to go from 1 to 8, we add 7, and to go from 8 to 15, we also add 7. That means we're adding 7 each time. So we get 22, 29, and then you guys can carry it on just adding 7. Okay, here it looks like we are subtracting 10 each time. So here we get 1, 0, 0, 1, 0. And if we subtract another 10, we get 1, 0, 0, 0, 0. If we subtract another 10, we get 9, 9, 9, 0. And then if you subtract another 10, you get 9, 9, 8, 0. So it does make sense. And then you can fill in the other ones over here. Over here, it looks like we are adding 1,5 to each term. So if we add 1,5 to 1,5, we get 3. If we add 1,5 to 4 to 3, we get 4,5. And if we add 1,5 to 4,5, we can get 6. 6, 0. And then 1,5 added to that, we can get 7,5. 1,5 added to 7.5 will give us 9, 0. And you guys can fill in the rest. And remember to write down the rule of the pattern. Okay, what are we adding here? Between 2,2, the difference between 2,2 and 4,0 is 1.8. So there's a difference between 1.8 between these two numbers, and the difference between 4 and 5,8 is also 1.8. So we're adding 1.8 to each number. So the next number we will get is 7,6. Then we will get 9,4. Then we'll get 11,2. And you guys can do the rest and write the rule. Don't forget to write the rule. Okay. Now we get 45 and 3/4. And the difference between that and 46.5 is, now we're going down for the first one. Sorry, going up for the first one. So we're adding looks like 3/4. We are adding 0.75. So if we add 3/4 to that, we will get 46.5. And if we add another 3/4 to that, so if we add 3/4 to 46.5, we will get 47.25. And then if we add 3/4 to 47.25, we'll get 48. Then over here, we will get 48 3/4. And if we add 3/4 to that, we will get 49.5. If we add 3/4 to that, we'll get 50.25. And I'll let you guys answer the rest by continuing the pattern. 50.25. Okay, now over here, we have a missing term, and then we go 100.49, and then we go 100.38, and we go 100.27. So it looks like we're going down in this pattern, and it looks like we're going down by 0.11. So if we go down by, let's first go up by 0.11. We will get 100.6. Then if we go down by 0.11 over here, 100, we'll get 100.16. And if we do that again, we'll get 100.05. Oh, that's 100.05. And if we go down, just to check one more time, if we go down another 0.11, we will get 99.94, it seems. Let me just check that. Yep, so our pattern is correct there. Complete the table below. So we have an input number, and then we have an input number plus 7. So we have 1 plus 7 gives us 8, 2 plus 7 gives us 9, 3 plus 7 gives us 10. And then you can already see a pattern developing by itself on the bottom, where we will have 12. Oh no, sorry, the pattern does not continue, it seems. 5 plus 7, okay, it does. And then it looks like we skipped something. So this doesn't necessarily correlate to 6. So we'll do the opposite here. What number plus 7 will give us 15? So this number 15 minus 7 gives us 8. Then 12 plus 7 gives us 19. 30 minus 7 will give us 23. And then n, so this is the input number n, and then we can generalize this statement at the bottom to be n plus 7. So it doesn't matter what the input number is, the number at the bottom will be n plus 7. So we have 5, and then over here we have n plus 7, so n is 5, n plus 7 is 5 plus 7, which gives us 12. Let's go on to the next page. Multiplying or dividing with the same number. Take another look at the sequence f. So we have 2, 6, 18, 54, 162, and 486. Pete explains that he figured out how to continue the sequence f. I looked at the first 2 terms in the sequence and wrote 2 times what is equal to 6. When I multiplied the first number by 3, I got the second number. So 2 times 3 is equal to 6. I then checked to see if I could find the next number if I multiplied 6 by 3. So 6 times 3 equals 18. I continued checking in this way. So 18 times 3 gives us 54. 54 times 3 gives us 162. 162 times 3 will give us 486. This gave me a rule I can use to extend the sequence, and my rule was multiply each number by 3 to calculate the next number in the sequence. And then it says, Zinsler says that you can also find the pattern by working backwards and dividing by 3 each time. So you can have 54 divided by 3, and then you get 18. 18 divided by 3 will give us 6, and 6 divided by 3 will give us 2. The number that we multiply with to get the next term in the sequence is called a ratio. If the number we multiply with remains the same throughout the sequence, we say it is a constant ratio. Check whether Pete's reasoning works for sequence H. 2, 4, 8, 16, 32, and 64. So we did this one earlier, I think. And you can, so we're going to see 2 times what will give us 4. 2 times, maybe I should use some different. 2 times what will give us 4? That will give us 2. 4 times what will give us 8? 2. 8 times what will give us 16? 2. And then you can carry on checking them. 16 times 2 give us 32. If we times 32 by 2, that will give us 64. So it's similar to sequence F, except now we are timesing by 3. So that means the next numbers would be 64 times 2, which would be 128, and then 256, and then 512. Okay, question 2. Describe in words the rule for finding the next number in the sequence. Also write down the next 5 terms of the sequence if the pattern is continued. Okay, so I want you guys to press pause and do this yourself. I'll also go through them with you though. So we've already been hinted that it's going to be multiplying or dividing. So we don't really have to look at addition between terms or subtraction. We're just going to see from the terms what times the first term will give us the second term, what times the second term will give us the third term, etc. for all of the sequences. So 1 times something will give us 10, and 10 times something will give us 100. So the answer is we are multiplying each one by 10, because 1 times 10 gives us 10, 10 times 10 gives us 100, and 100 times 10 gives us 1,000. So then the next 3 would be 10,000, and then 100,000, and then 1 million. Okay, now we look at sequence B. So 16 times what will give us 8? 8 times what will give us 4? And 4 times what will give us 2? So 16 divided by 2 will give us, 8. And then 8 divided by 2 will give us 4. And 4 divided by 2 will give us 2. So using that logic, we can get the next term in the sequence will be 1. The next term in the sequence will be a half, because we are dividing by 2. And the next term in the sequence will be a quarter. Now we look at sequence C, and we go from 7 to minus 21 to 63 to minus 189. So 7 times what will give us minus 21? 7 times minus 3. So I'll write here, minus times minus 3 will give us minus 21. And then minus 21 times minus 3, which will give us a positive, remember, because if you multiply a negative by a negative, it becomes a positive. Then you'll get 63. And then again, if you multiply 63 by minus 3, you get 189. And then if you multiply 100 minus 189, sorry, that was the answer, minus 189 by minus 3, you'll get 567. And if you times that by minus 3, you get the next term, which is minus 1,701. And if you times that by 3, you'll get the next term, which will be 5,103. And then if we move on to sequence D, sequence D goes 3, 12, and then 48. So 3 times what will give us 12. 3 times 4 will give us 12. And then we can check 12 times 4 gives us 48. Then 48 times 4 will give us 192. 192 times 4 will give us 768. And 768 times 4 will give us 3,072. Then we have 2,187 minus 729, 243, and minus 81. So let's just, for one example, I could have done it on an earlier one, but you can also use a method going backwards. So like this method over here, they went this way, so they went this way on the sequence. That's an arrow. Then they're going backwards and seeing what it can be divided by or times by that way. So if we start over here at minus 81 times what will give us 243. And the answer is minus 3. So then, but because we've worked backwards, we went this way as times, then this way will be divide. So the answer will be, we are dividing the terms going this way by minus 3. And we can check that quickly. So 2,187 divided by minus 3 will give us minus 729. Okay, so that works. And if you divide that by minus 3, you get 243. If you divide that by minus 3, you get minus 81. And if you divide that by minus 3, you get 27. That divided by minus 3 give us minus 9. Wow, that's a long minus. Minus 9. And that divided by minus 3 will give us 3. There we go. Fill in the missing output and input numbers. Okay, so these are the input numbers. So 1 times 6 will give us 6. 2 times 6 will give us 12. 3 times 6 will give us 18. And then something times 6 will give us 24. What is that? That is 4. 4 times 6 equals 24. 5 times 6 will give us 13. Okay, 13. Something times 6 will give us 36, which would be 6. 6 times 6 is equal to 36. 7 times 6 is going to be equal to 42. What is the term-to-term rule for the output numbers here? Plus 6 or times 6? It is times 6. Oh, term-to-term rule, sorry. I think that means this way, going this way. So the difference between these terms is plus 6. Complete the table below. So we have input numbers here and output numbers down here. So it looks like we have the exact same thing that we have over here. We have 1 is an input and 6 is an output. So that looks like 1 times 6, and then we have 4 as an input and 24 as an output. So that looks like 4 times 6. So then we can assume that each number is getting times by 6. So then we have the same results as over here. So we have 12, 18, 24, 30, and then 6 times 6 will give us 36. We write a 6 up there. 12 times 6 will give us 72. And then what we have is we have over here x, this is the general form, times, actually I'm not going to write it as x times 6, I'm going to write it as 6x, which is the same as 6 times x, or x times 6. Neither adding nor multiplying by the same number. Consider sequences A to H again and answer the questions that follow. Which sequences are the same kind as sequence B? In what way are the sequences B and E different from the other sequences? Okay, these are questions for you guys to answer. And then it says here, there are sequences where there's neither a constant difference nor a constant ratio between the consecutive terms, and yet a pattern still exists, as in the cases of B and E. So B, remember, I think this is the odd numbers getting added. So we have 1, then 3, then 5, 7. Consider the sequence 10, 17, 26, 37, and 50. Write down the next 5 numbers in the sequence. Okay, so how we would do this is we would see what is the difference between 10 and 17? 7. The difference between 17 and 26? 9. The difference between 26 and 37? 11. And the difference between 37 and 50? 13. So we're going up in odd numbers. So if we add 15 to 50, we'll get 65. And then if we add, so then that there will be a difference of 15 here to get to 65. Then the next difference will be 17. And the next difference will be 19. So that is how it is going up in this case. So if we add 17 to 65, we will get 82. And if we add 19 to 82, we will get 101. Eric observed that he can calculate the next term in the sequence as follows. So 7 plus 10 is equal to 17. 17 plus 9 is equal to 26. 26 plus 11 is equal to 37. Use Eric's method to check whether your numbers in question A above are correct. Okay, so we use the same method, so we're going to assume that these numbers are correct. But please check them. This is 101, so that's a 0. Yes, that's not very clear. 101. Which of the statements below can Eric use to describe the relationship between the numbers in the sequence in question 2? Test the rule for the first 3 terms of the sequence and then simply write yes or no next to each statement. So increase the difference between consecutive terms by 2 each time. Yes. Increase the difference between consecutive terms by 1 each time. No. Add 2 or more than you added to the previous term? No. Please check these and make sure they're correct. Provide a rule to describe the relationship between the numbers in the sequences below. Use your rule to provide the next 5 numbers in the sequence. Okay, so I'm not going to do all of these, I don't think. But the difference between these terms here is 3. Then the difference between these terms is 5. The difference between these terms is 7. So it looks like we're going up in odd numbers. And the difference between these terms is 9. So then we can add 11 to 25. It'll give us 36. So 36 is the next term. And then we're going to add 13, which gives us 49. And then we're going to add 15 to 49 to give us 64. Okay, I'm going to leave the rest of these questions up to you guys on this slide. Please complete them. The position-term relationship in a sequence. Using position to make predictions. Take another look at sequences A to H. Which sequences or sequence are of the same kind as sequence A? And then explain. So I'm going to leave that up to you guys to do. Cesware has been thinking about Amanda and Tamara's explanations of how they worked out the rule for sequence A and has drawn up a table. He agrees with them, but says that there's another rule that will also work. He explains as follows. My table shows the terms in the sequence and the difference between consecutive terms. So, okay, then this will be the fifth term. This will be the sixth term. Seventh, eighth, ninth, and 10th. Okay, so we're looking at the terms. So remember, we're looking at sequence A over here. Looks like they left out the 2, but anyway, starting from 5, we have 5, 8, 11, 14, etc. And the differences here are we adding 3 each time. So we get 17, we get 20, we get 23, we get 26, we get 29, and we get 32. Okay, so that is just to clarify quickly. This method is what I've been showing you when I do something and I go like this and I show like the loops. That is just showing the difference between the terms. So here we have 4, sorry, we don't have 4, we have 2, then 4, then 8, whatever. But yeah, it's just, that's what those loops mean when I'm drawing them. These were reasons that the following rule will also work. Multiply the position of the number by 3 and add 2 to the answer. I can write this rule as a number sentence. Position of the number times 3 plus 2. Okay, so the position of the number is where the term is. Okay, so the first term will go the position 1 times 3, 3. So 1 times 3 gives us 3, plus 2 gives us 5. So that is the number sentence. I use my number sentence to check. 1 times 3 plus 2 gives us 5. 2, so now we're looking at the second term. 2 times 3 gives us 6, plus 2 gives us 8. Then the third term, we look at 3 times 3, so 3 from the third term, times 3 gives us 9, plus 2 gives us 11. Okay, so how this works is you find the difference between each term, because I'm sure at some stage you'll be asked to write the answer as a number sentence. So the position of the number could also be written as n, let's say. N times 3 plus 2. So this is how it could be written. And then you can get any number in the sequence. So n is just the term number. So if we throw a 4 in there, if we put a 4 in the n, and we go 4 times 3, that gives us 12, plus 2 gives us 14. And we can check, yep, the fourth term is 14. So how we do this is you always find the difference between the terms first, okay? And then what you do is you go the difference times the first term, so you'll get 3, and then you need to see what can be added or subtracted to get the first term actual number. So you'll just, because n will be 1 for the first term, so it would just be 3 times n, and then you need to see what can be added or subtracted to get the first term. I'll hopefully explain that in more detail just now if we get another example. What do the numbers in bold in Caesar's number sentence stand for? So these numbers here, these stand for the term, the number, so like which term it is. I'm just going to write term. So it stands for the term. What does the number 3 in Caesar's number sentence stand for? So that is the difference. Okay. Consider the sequence 5, 8, 11, 14. Apply Caesar's rule to this, the sequence and determine the number 7 of the sequence, term number 7, sorry, term number 10 of the sequence, and the 100th term of the sequence. Okay, so now let me try explain properly how to do this. So we find the difference first. Okay, actually, before we do this, just so, okay, these are the terms in red. Okay, terms. Okay, so this is the first term. Oh, I'm not going to write it like that. 1. Okay, this is the second term. This is the third term. And this is the fourth term, etc. Okay. But now we want to find a rule for each term. So first, we find the differences between each term. So the difference between 5 and 8 is 3. The difference between 8 and 11 is 3. And the difference between 11 and 14 is 3. And you can do that by doing this and just drawing it out if you have enough space, just so it's really clear. 3, 3, 3. So I'm just going to erase that because it's taking up a bit much space. So then we're going to write over here, differences is equal to 3. So now how we do it is we use the differences. Okay, and this is also equal to n in this case. Okay, so how we would start writing our number sentence is n times the differences times 3, and then we're either going to add or subtract. So let's say plus. Okay, so now what we have, so for the first term, if n is equal to 1, we're going to get 3. So now we need to add or subtract something to get the actual first term number, which is 5. So if n is 1, n times 3 gives us 3. So we're going to add 2 to get 5. I hope you guys are following. So the terms in red is n. The differences is the difference between the numbers. And then we use those. So we go n times the differences, and then we're going to add or subtract something to get an expression that can answer like any of these terms. So basically we can answer any number in the pattern just by replacing n. So if n is 1, 1 times 3 gives us 3, plus 2 gives us 5. Now we're going to check it, okay? Now n is 2, and we expect an answer of 8. So 2 times 3 gives us 6. Okay. Plus 2 gives us 8. Okay, so that means it works for the second term. And let's check it for the third term and the fourth term. For the third term, it'll be 3 times 3 gives us 9, plus 2 gives us 11. It works for the third term. For the fourth term, it'll be 4 times 3, which gives us 12, plus 2, which gives us 14. So that means it works for the fourth term as well. So now we have a very useful expression to work out any the value of any term in the sequence. So now all we have to do to answer these questions is, so term number 7, what is the value? We just put a 7 in there. So we go 7 times 3, which is 21. And then we add 2. So we're going to get 23 is this answer. term number 10, we have 10 times 3, which gives us 30. So you just put a 10 where the n is. 10 times 3, which gives us 30, plus 2, which gives us 32. The 100th term is going to be 100, because that's the n, times 3, which gives us 300, plus 2. So it'll be 302. Consider the sequence 3, 5, 7, 9, 11, 13, 15, 17, 19. Use Caesar's explanation to find a rule for this sequence. Okay, and I've shown you how to find a rule, showing you step by step how to find the rule for Caesar's sequence over here. So press pause, please try to do this by yourself first, and then I'll go through it again with you now. Okay, I hope you managed to find the sequence. So again, I'm just going to write the term numbers over here. So sometimes this is useful. This is not the differences, please remember. This is just what the term number is. Okay. Now we look at the differences, and this is the same as n, okay? N, and we're going to have n times something. And the differences over here. So the difference between 3 and 5 is 2, between 5 and 7 is 2, between 7 and 9 is 2, 9 and 11, 2, 11 and 13 is 2, etc. So the differences, which I'm just going to write as d now, is 2. So we have n times 2 now, plus something, and this will give us our sequence rule. So if we put 1, if n is 1, then 1 times 2 will give us 2, plus what will give us 3, because n is 1, the first term, and we need to get 3. So plus 1. So now let's check it for n is equal to 2. Let's hope this works. So now we think we have our rule, but we always need to check it. So now n is equal to 2. So now we are hoping we get an answer of 5. So these are the n's, remember, the reds are the n's. Now we're hoping we get an answer of 5. So 2 times 2 gives us 4, plus 1 gives us 5. And let's check one more, check a random one. We can check with 7. 7 times 2 gives us 14, plus 1 gives us 15, which is correct. So there's our rule. Our rule is n. This is the answer for this question here. N times 2 plus 1. And then to determine the 28th term of the sequence, we substitute 28 into n, which will be 28 times 2, which gives us 56 plus 1. So the answer will be 57. More predictions. Complete the tables below by calculating the missing terms. Okay, so I'm going to let you guys do these questions. Hope you know how to find the rule for a sequence now. Okay, let's look at maybe this one. So the difference between these is 12. And the difference between 15 and 27, I think it's also 12. It is 12. So that means the differences are probably constant, and that all of them will be 12. So we won't be 12 between here though, because 4 and 7 aren't consecutive positions. So there'll be a larger difference here. But we can get the next term after 3 by just adding 12 to 27, which gives us 39. And then we can find the rule by going n times 12 times 12, and then it will be minus 9. And you can check that by substituting n. So n is the position in the sequence. So let's substitute 1 in. We get 1 times 12 minus 9, which gives us an answer of 3 as the term. And if we substitute 2 in, we get 2 times 12 minus 9, which gives us 15. And then we can substitute any number in to get an answer. So let's use this to find term number 7. So 7 times 12 is equal to 84, minus 9 is equal to 75. And then for the 30th term, we sub 30 in for n. 30 times 12 minus 9 gives us 351. That's a 51. Use the rule position in the sequence times position in the sequence plus 1 to complete the table below. So position in the sequence. So now this is not 100% convention. You can maybe your teacher will prefer something besides an n here. N just makes it simple for me instead of writing position in the sequence. And then we're going to times it. So what this is going to be n times n plus 1. Okay, so that is essentially what it's saying. And we know that n is the position in the sequence. So for the first one, we have 1 times 1 plus 1, which is 2. So 1 times 2. Then if we substitute a 2 in there for n, we have 2 times 2 plus 1, which is 3. So we're going to get a 6. Then if we substitute a 3, we're going to have 3 times 3 plus 1, which is 4. 3 times 4, 12. We have a 4 substituted for n. We have 4 times 4 plus 1, which is 5. 4 times 5 gives us 20. We have a 5. We have 5 times 5 plus 1, which is 6. 5 times 6, which is 30. If we have a 6 for n, we have 6 times 6 plus 1, which is 7. 6 times 7 gives us 42. There we go. Investigating and extending geometric patterns, square numbers. A factory makes window frames. Type 1 has 1 window pane. Type 2 has 4 window panes. Type 3 has 9 window panes, and so on. So we have 1, 4, 9, 16. How many window panes are we there in type 25? Type 5. And if you look at this, this is just the square numbers. So it's the type squared. 3 squared is 9, 4 squared is 16, 2 squared is 4, 1 squared is 1. So 5 squared is 25. 6 squared is 36. 7 squared is 49. And 12 squared is 144. And the explanation is 12 times 12 is equal to 144. Complete the table and show your calculations. So the number of window panes is just the frame type squared. So 15 squared is going to be 225. So your calculations can be 15 squared or 15 times 15 to get 225, and 20 squared or 20 times 20 gives us 400 window panes. In algebra, we think of a square as a number that is obtained by multiplying a number by itself. So 1 is also a square because 1 times 1 is equal to 1. 2 times 2 gives us 4. 3 times 3 gives us 9. 4 times 4 or 4 squared gives us 16. 5 squared or 5 times 5 gives us 25. The symbol n is used below to represent the position number in the expression that gives the rule n squared when generalizing. Okay, so that's what we've been doing before. So this is the term number. So if we had to get our red pen, just so you guys remember, this would be the first term, second term, the third term, the fourth term, and the fifth term. Okay, and then this would be the nth term, and this would be the expression to get any number. So this would be how you would find how many window panes are in a type. Now we look at triangular numbers. These circles, sorry, what does it say? I don't know. Uses circles to form a pattern of triangular shapes. Oh, this is a person, Teresa. Sorry, I thought it was a spelling error. So Teresa uses circles to form a pattern of triangular shapes. Picture 1, picture 2, picture 3, and picture 4. So in picture 1, we have 1 circle. Picture 2, we have 3. Picture 3, we have 1, 2, 3, 4, 5, 6. Picture 4, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. If the pattern is continued, how many circles must Teresa have? In the bottom row of picture 5. The bottom row of picture 5 will have 5. So you can see the bottom row is also the number of the picture. So 2 for picture 2 has 2 at the bottom row, picture 3 has 3 at the bottom row, picture 4 is 4 at the bottom row. So the bottom row has 5 in picture 5. The second row from the bottom of picture 5. So I think that will be 1 less than 5, so it'll be 4. And then the third row from the bottom will be 3. The second row will be 2. And the top row is always 1, as you can see. So we have a triangle going 5, 4, 3, 2, 1. So you could actually draw picture 5 by just adding on 2, 3, 4, 5 at the bottom, and then that would be picture 5. Horrible drawing, but you get the idea. In total, in picture 5, show your calculation. So how many would there be? And you just add these up, all the different rows. So it would be 15, because it'll be 5 plus 4 gives us 9, plus 3 gives us 12, plus 2 gives us 14, plus 1 gives us 15. How many circles does Teresa need to form triangle picture 7? Show the calculation. So for picture 5, we just went 5 plus 4 plus 3 plus 2 plus 1. So it'll be the same for picture 7. It'll be 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. And that would give us 28. How many circles does Teresa need to form triangle picture 8? I would say 36, because it would be picture 7 plus 8 at the bottom. So 36. Complete the table below, show all your work. Okay, so this would be 15, 21. Okay, we would probably need to find a rule for this question. I'm going to leave that up to you guys to calculate the rule. Yeah, because this lecture is dragging on quite a bit. More than 2,500 years ago, Greek mathematicians already knew that the numbers 3, 6, 10, 15, and so on could form a triangular pattern. They represented these numbers with dots, which they arranged in such a way that they formed equilateral triangles, hence the name triangular numbers. Algebraically, we think of them as sums of consecutive neutral numbers starting with 1. Let us revisit the activity on triangular numbers that we did on the previous page. So far, we have determined that the number of circles in the pattern by adding consecutive neutral numbers. If we were asked to determine the number of circles in picture 200, for example, it would take us a very long time to do so. We need to find a quicker method of finding any triangular numbers in the sequence. Consider the arrangement below. We have added the yellow circles to the original blue circles and then rearranged the circles in such a way that they're in rectangular form. Picture 2 is 3 circles long and 2 circles wide. So this is the length and this is the width. Complete the following sentence. Picture 3 is 4 circles long and 3 circles wide. Picture 4 is 5 circles long and 4 circles wide. Maybe I should write them in. Picture 3 is 4 circles long and 3 circles wide. Picture 1 is 2 circles long and 1 circle wide. Picture 4 is 5 circles long and 4 circles wide. Picture 5 would be 6 circles long and 5 circles wide. How many circles will there be in a picture that is 10 circles long and 9 circles wide? So that is just 10 times 9, so 90. And then 7 long and 6 wide would be 7 times 6, which is 42. 6 long and 5 wide, 30. 20 long and 19 wide, 20 times 19, 380. Suppose we want to have a quicker method to determine the number of circles in picture 15. We know that picture 15 is 16 circles long and 15 circles wide. This gives a total of 15 times 16, which is 240. But we must compensate for the fact that the yellow circles were originally not there by halving the total number of circles. In other words, the original figure has 240 divided by 2, or 120 circles. Use the above reasoning to calculate the number of circles in each. So in picture 20, so we know picture 20 is 19, sorry, let me just check here quickly. Okay, so picture 20 will be 21 long and 20 wide. But then we need to divide that by 2. So 21 times 20 will give us 420. And if you divide that by 2, because we are getting rid of the yellow circles, so if we divide that by 2, 420 divided by 2, we'll get 210. Picture 35 is 36 long and 35 wide. 36 times 35 is 1,260. And we need to divide that by 2, 1,260 divided by 2. Which is equal to 630. Okay, let's move on. Describing patterns in different ways. T-shaped numbers. The pattern below is made from squares. How many squares will there be in pattern 5? Okay, so let's first look here. Pattern 1, we have 1. Pattern 2, we have 1, 2, 3, 4. Pattern 3, we have 1, 2, 3, 4, 5, 6, 7. Yeah, 7. Pattern 4, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks like we're going up in threes between 1 and 4, 4 and 7, and 7 and 10. So I would say the next one is 13 for the fifth one. So it'll be 13 squares in pattern 5. And then for pattern 15, we'd have to find a generalization. So the differences, so if we get our color pen and we say D is equal to 3, then we could write n times 3, and in this case we would be subtracting 2 from each term. So if we substitute 1 in there, we have 1 times 3 gives us 3 minus 2, which would give us 1. Then for the second term, we would have 2 times 3, which gives us 6 minus 2, which gives us 4. So then we can substitute 15 in here to find out how many squares will be in pattern 15. So we have 15 times 3, which gives us 45 minus 2, which gives us 43. And then we can use this rule to answer any of these questions. So for 5, we can substitute 5 in. 5 times 3 minus 2 gives us 13. And then for 6, 6 times 3 minus 2 gives us 16. And then for 20, 20 times 3 minus 2 gives us 58. Below are 3 different methods or plans to calculate the number of squares for pattern 20. Study each one carefully. So plan A is to get from 1 square to 4 squares, you have to add 3 squares. To get from 4 squares to 7 squares, you add 3 squares. To get from 7 squares to add 10 squares, you add 3 squares. So continue to add 3 squares for each pattern until 20. Plan B, multiply the pattern by 3 and then subtract 2. So pattern 20 will have 20 times 3 minus 2. That's the one we used. Or plan C is the number of squares in pattern 5 is 13. So pattern 20 will have 13 times 4, which is 52 squares, because 20 is equal to 5 times 4. So in this case, you're going to have 4 of the patterns that look like pattern 5. You're just going to have 4 of them, and then you'll add up those squares. That's essentially what that calculation is doing. Which method, A, B, or C, will give the correct answer? So all of them will give the correct answer. Oh no, doesn't seem so. Plan C does not give the correct answer. Assuming our method is correct of 58, which I think it is. And then which one of the plans did we use? We used this one, unless you did the question before and used a different plan. And if mine is incorrect, then please explain why. Can the flow diagram be used to calculate the number of squares? So we have an input and then an output. 3 figures are given below. Okay, so maybe we should check. Or actually, you guys use this to check. So, and some other shapes. 3 figures are given below. Draw the next figure in the tile pattern. Okay, I want you guys to do that. It's going to be very difficult for me to draw that. If the pattern is continued, how many tiles will there be in the 17th figure? Answer this question by analyzing what happens. So analyzing what happens is maybe just counting up the tiles and then coming up with the rule. Tato decides that it is easier for him to see the pattern when the tiles are rearranged, as shown here. Okay, so he rearranges the tiles to make it easier to see. Now I'll use Tato's method to determine the number of tiles in the 23rd figure. Okay, looks like there's also a calculation here. So I would say that this term here is the pattern number. So this is pattern number 1, this is pattern number 2, and this is pattern number 3. So if we substitute 23 in there, that should give us the correct answer. So we'd have 3 times 23 plus 2, which gives us 71. So I would say that the answer here would be 71. Please check that though. Complete the flow diagram below by writing the appropriate operations so that it can be used to calculate the number of tiles in any figure of the pattern. So we have 1 times something. So I would go 1 times 3 plus 2, which gives us 5. 1 times 3 gives us 3, plus 2 gives us 5. 2 times 3 gives us 6, plus 2 gives us 8. 3 times 3 gives us 9, plus 2 gives us 11. 17 times 3 gives us 51, plus 3 gives us 52. And sorry, 51 plus 2 gives us 53. How many tiles will there be in the 50th figure if the pattern is continued? So we could just substitute in here. 50 times 3 is 150 plus 2, 152. And here's a worksheet for you guys to do. Press pause. This is for you guys to complete on your own. And that is the end of today's lesson.